So far we've been dealing with multivariable functions and understanding how the notation works, how we could visualize three-dimensional functions, and now we want to start to understand how does the output change when one of the inputs changes. So the difference here as compared to univariate functions, functions with one input, now we have to ask this question twice. Specifically, when we have two input variables, we want to ask, how does one input affect the output, and how does the second input affect the output? Let's take a look at an example. The cost C to rent a moving truck is a function of the number of days D that it is rented for, as well as the number of miles the truck is driven for while rented. And let's suppose that this cost function right here describes that relationship. C of D comma M equals 20D plus 0.5 M. And so what we want to know is, how do D and M affect the change in C? In other words, what is the price per day and what is the price per mile, or the cost per mile? Well, as we begin investigating this, we see that this is going to be something that we could plot in three dimensions. And on one axis, we could have arbitrarily call this D and call this M. And this axis will represent our cost. And so we could say, for example, if we rent the truck, but we rent it for 0 days and 0 miles, C of 0 comma 0 will equal 0. And so that makes sense, because that means that when you basically don't rent the truck, you don't have any cost associated with the truck rental. But as we begin kind of unpacking this and thinking about what happens if we only change D, in other words, what is the change in cost per change in day? So I'll write it like this. I'll say the change in cost per change in day. Well, let's focus on fixing the value of the other variable. So let's suppose that we let M equal 100. Well, that means that our function, or our reduction of this function, will be C of D comma 100 equals 20D plus 50. And now we can see that this is just a linear function in 2 dimensions that I could actually graph. And I could write it like this. I could say, well, here is the cost versus the distance for M equals 50, sorry, not 50, M equals 100 miles. So if I rent the truck for 100 miles, I'll get a function that has a vertical intercept of 50. It'll be a linear function that has a slope of 20 to 1. And so at this point I might say, oh, well, that means that for each additional day, results in $20 of additional cost. So as I move 1 unit in the direction of D, I have to move up 20 units in the direction of C. And since D represents days and cost represents, C represents cost in dollars, that means we're looking at $20 per day equals $20 per 1 day. Now the value of M that I gave it really didn't matter, because if I consider M equals, let's say, 200, then my cost function becomes C of D comma 200, which is 20D plus 0.5 times 200, which will simply be 100. And that's the same function, just shifted up 50 more units. But it has the same slope. It still has a relationship of every additional day will result in an increase of C in cost of $20. And so that's how I can start to unpack this a little bit, by thinking about how does only the change in one input affect the output. when I'm holding the other one constant. And we can all agree is if I begin changing d and m at the same time, I'm not going to be able to determine, based on just the total cost, how much influence d had on that cost and how much influence m had on that cost, unless I begin thinking about this as one variable being held constant. So here we're saying hold m constant. And we can do this all day long. I can put in m equals 300, m equals 400, but the slope in the d direction is still going to be 20 to 1. Now let's look at the other possibility, which is what happens when we change m. In other words, we want to look at the change in cost per change in mile. This means we're going to have to hold d constant. We're not going to allow it to influence our interpretation of how does each additional mile change our cost. So let's just hypothetically say we set days to be 1, and then our function c of 1 comma m will be 20 times 1, which is 20, plus 0.5 m. So I could write this as 0.5 m plus 20. And when I graph that, I see that that's now a relationship between cost and miles. We have a vertical intercept of $20, and then our slope is going to be 0.5. So I'm going to draw that as a fairly low inclined line where 1 unit of m creates a change in c of only 0.5. Well, that right there tells me that each additional mile results in 50 cents of additional cost. So that allows me to conclude that the cost per mile is 50 cents per 1 mile. Now that again won't change if I rent this truck for 2 days and fix the number of days at 2. Then my function will be the same, except I'll have 0.5 m plus 40. And that should make sense because each day is costing us 20 bucks. So if I rent the truck for 2 days, that's going to cost me $40 for the 2-day rental plus the cost for the miles. And we can see that already we're talking about the rate at which cost changes based upon a 1 unit change in the other variable. And this is very valuable because we see how each input may influence our output. Now, if we're talking about profit, well, we could start to investigate, for example, how does advertising, every dollar we spend on advertising, how much impact does that have on our cost? Or how much does hiring a new employee have on our cost or profit? So the idea of rate of change here is to always hold something constant, whether that would be m or d. We hold the variable constant that we don't want to study and then explore the impact between cost and the other variable. So these two graphs can be thought of as cross-sections for holding one variable constant. So this one here would just be the exact same graph, same slope and everything, still a 0.5 to 1 relationship, and holding that other variable constant just gives us that fixed overhead of $40. Now before we get into talking about derivatives, because here we didn't need to use any derivatives since we're dealing with constant rate of change. But constant rate of change is not always true. We often have functions that may change variably. For example, let's take a look at this situation here. We're going to study the impact of the difference between average rate of change and the derivative. So suppose the following graph shows the distance you have traveled from home as a function of time. Now, the means by which we're traveling, we're probably not traveling by car because we see that after 3 hours, we've only done about 10 miles. So let's say that we want to figure out maybe between time 0 and time 3, how fast are we traveling? What's our rate of change? In other words, what's our change in distance per 1 unit change in time? That answer is going to be different because we see that this is not a straight line. In fact, as we get closer to time 3, we see that the curve is starting to flatten, which means the speed must be slowing down. If notice in a 1 hour time period here, we're only doing about 1.5 miles. Right? That change from here is roughly about 1.5 miles of distance. But we see that from time 0 to time 1, we did about 5.5 miles. And that's a much faster, a much bigger speed. We were traveling faster at that point. Now, if I want to look at the average rate of change over the first 3 hours, what I could do is think about a linearization of this. So if I were traveling at a constant rate of change, this line would represent my change in distance. And we can see that that's actually kind of off because here we're traveling really fast, here we're traveling a lot slower, and here somewhere in the middle we're traveling at about the slope of this line. So if I imagine that this is roughly the point 3, 10, and this is the point 0, 0, then the change in distance is this length right here, right? That's the total distance between these 2 points. 10 minus 0, that's 10 miles. And the change in time was 3 hours. So 10 miles, 3 hours, and so I get roughly 3.33 miles per 1 hour. So if I do that division, that amounts to 10/3 miles per hour, 3.33 miles per hour. But if really what I was interested in is how fast was I going when I left my house, so this right here is the average speed over the interval 0 less than or equal to t less than or equal to 3. That's the average speed or the average rate of change. But what was my, if I were to get flagged by a radar that told me my instantaneous speed, or I looked at my speedometer, then what I would want to know is what is my instantaneous rate of change? Or in other words, my derivative. That's the word we use to represent instantaneous rate of change, or my speedometer speed at that moment. Okay, well, we've already argued this fact that here I'm kind of going slow, and I'm going to draw a line that kind of represents the line that is tangent to that curve. And I can see that the slope of this line right here is much smaller than the slope of this line. But right here, I can see that the slope of that line represents a high speed compared to here where I'm going at a low speed. And as time passes, we can see that that's the slope of that tangent line. This is kind of more of a medium speed, which looks a little bit more like our average speed, roughly speaking. And we see that if we kind of draw slopes along the way, we see that the slopes of those lines are slowly starting to get flatter and flatter and flatter and flatter as we reach our maximum distance. And then it looks like we're going to turn back around and go home. So the instantaneous rate of change, in other words, how fast were we going? Were we going at exactly at the instant t equals 0? Well, this function is approximately, or the actual function is with some rounding, d of t equals negative t squared plus 6.3t. And we've learned before that the derivative can be found by what we call the power rule, which would be called d prime of t. And the power rule states that if you take the derivative of, say, x squared, the derivative of x squared would be 2x. So we multiply by the current exponent, which is negative 2 times t. It sort of drops down, if you will. And then we subtract 1 from the exponent. The derivative of 6.3t to the first would kind of be the same thing. 6.3 times 1 is 6.3. And then subtract 1 from the exponent would be 0. In other words, the slope of 6.3t is just 6.3, because t to the 0 is 1. So negative 2t plus 6.3. So this is our derivative function. And what this gives us is the change in distance over the change in time. The notation we use here is, instead of using delta, which is reserved for average rate of change over a wider interval of time, we would often write this like this. Instead of using delta, which is the Greek d, we actually use this lowercase d to indicate that this is instantaneous. So the instantaneous speed at any given time can be found by taking negative 2t plus 6.3. So at time 0, which is this instant right here, I can plug in 0 for t, and sometimes you'll see it written like this. It'll be negative 2 times 0 plus 6.3, which equals 6.3. Now that number, 6.3, is the change in distance over change in time. So let me put this over 1. And the 6.3 is then the change in distance, which is in miles. And the denominator is the change in time, which is measured in hours. And so I can say that at t equals 0, I am traveling at an exact speed of 6.3 miles per hour. And we can see that that is definitely faster. As we had predicted, we see that the slope of that tangent line, which the slope of this tangent line is 6.3, we see that we're traveling a lot faster at first than we are later on. So let's just double check that. For example, at t equals 2, which is roughly right there, that speed should be lower. That instantaneous, that radar speed at that instant, at t equals 2, will be negative 2 times 2 plus 6.3, which is going to be 2.3 miles over 1 hour. So we are slowing down. But our average speed, notice, it was in between the highest and the lowest speed, because on average we were traveling 3.33 miles per hour. At some points we were actually traveling fast, and then maybe if this is we took a 3-hour jog, which is a long jog. We took a 3-hour jog. At first we were really chipper and running really fast, and then eventually by the time we got to that 3-hour mark, we were pretty slow. In fact, after 2 hours, we're kind of at a walking speed. Maybe we decided to walk at that point. And so anyway, the theme of all of this is that we are able to talk about the rate of change of a function based upon holding something constant in the multivariable realm. We looked at the idea of what's the difference between an average rate of change and an instantaneous rate of change, and what we ultimately want to go with is the idea of a derivative. In fact, we're going to be able to show that the derivative of this function right here, well, there are two. There's one with respect to days and another one with respect to miles. but we're going to find out that the derivative of cost with respect to days is 20, and the derivative of cost with respect to miles is going to be 0.5.